Welcome, class. If you really want to get a handle on advanced motor control, you have to start with the model. Today, we're going to build the most critical part of that model from the ground up, the complete inductance of a three-phase induction machine. Trust me, if you want to understand how modern drives really work, this is where it all begins.
So, here's our game plan. We're going to start with this stator, building it up, piece by piece, from a single phase to the complete model. Then, we'll get to the really interesting part, figuring out how to model that complex squirrel cage rotor and derive its inductance. And finally, we'll tie it all together and talk about why this is so critical for any real-world motor control.
You know, every complex model really starts with a simple assumption. For us, that means we're going to look at the stator by powering up just one phase, phase A. And we'll just imagine the rotor is there, but let's say it's electrically switched off, or open-circuited. This is a great trick because it lets us focus purely on the stator's own magnetic properties first.
Okay, take a look at this. This is the physical reality we need to model. When we push current through that phase A winding, it creates a magnetic field. But look closely here. That magnetic flux doesn't just take one single path. It actually splits. And really understanding these two different paths, well, that's the key to this entire model.
It is absolutely critical to get the difference between these two. The magnetizing flux, that's our workhorse. That's the good stuff that crosses the air gap to interact with the rotor, and that's what's essential for creating torque. The leakage flux, on the other hand, well, it's an unavoidable imperfection. Think of it like a parasitic effect that takes a shortcut and completes its path without ever linking the rotor. We have to account for both.
And here's how we translate that physical reality right into a beautifully simple equation. The total self-inductance of that one phase is just the sum of its two parts, the leakage inductance, LLS, and the magnetizing inductance, LM, one phase. See? It's a perfect one-to-one mapping from the physics to the math.
Now, what's so powerful about this is that we can calculate this magnetizing inductance directly from the machine's physical blueprints. This formula literally connects things you can measure with a ruler, like the rotor's radius, its length, or that tiny air gap, directly to an abstract electrical property. This is where mechanical design truly meets electrical performance.
So we've defined the self-inductance for just one phase, but of course, in a three-phase machine, these phases don't operate in a vacuum. So let's move to the next logical step and see how the current in one phase actually induces a voltage in the others. This right here is the whole concept of mutual inductance.
Look at those magnetic field lines again. The magnetizing flux from phase A, it doesn't just link up with the rotor. A big chunk of it inevitably links with the windings of phase B and phase C as well. This flux linkage, coming from a current in another phase, is exactly what defines mutual inductance.
Now, the beautiful thing here is that this interaction isn't random at all. It's perfectly predictable. And that's because the machine is designed with an incredible amount of symmetry. The windings are placed in this perfect sinusoidal pattern all the way around the stator. This physical symmetry is exactly what allows us to create such a beautifully simple mathematical model.
And here is where that symmetry just pays off wonderfully. The math directly reflects the physical layout. Because phase B is exactly 120 degrees away from phase A, the mutual inductance is simply the magnetizing inductance times the cosine of 120 degrees, which, of course, is -1/2. It really is that simple. All right, we now have the two essential building blocks, the self-inductance of one phase and the mutual inductance between phases. Now we can finally assemble these parts to create a complete and frankly much more useful per-phase inductance model for the entire stator when it's operating under balanced conditions.
So how do we combine all these different effects into one useful number? Well, let's walk through it. First, we write out the total magnetizing flux for phase A, which is a mix of its own inductance and the mutual parts from phases B and C. Next, and this is the key step, we use the fact that in a balanced system, the three currents always sum to zero. This lets us simplify things a lot. And after the math all shakes out, we're left with a new single term we call LM, which is just 3/2 times our original value. This is now our effective magnetizing inductance for one phase when the whole system is up and running.
And this brings us to our final, beautifully simple equation for the stator. The total stator inductance per phase, LS, is just the sum of its leakage inductance, LLS, and this new, comprehensive per-phase magnetizing inductance, LM. See that? All of those complex mutual interactions are now neatly bundled right into that LM term.
Excellent. We've got a complete model for the stator. But now we turn to the rotor. And if you've ever actually seen one,
You know a squirrel cage rotor, with its solid bars and end rings, looks nothing like the neat, tidy windings of the stator. How in the world do we even begin to model its inductance?
This is a real modeling puzzle, right? A squirrel cage doesn't have any obvious turns or phases like the stator does. So how do we even apply our framework? Well, the solution isn't to analyze it directly. It's to make a brilliant conceptual leap that simplifies the entire problem.
And here it is. This is that brilliant leap. We simply decide to model the squirrel cage as if it were an equivalent set of three-phase windings, just like the stator. Now, you might be asking, why are we allowed to do that? Because magnetically, the stator doesn't know the difference. It only sees the total magnetic field that the rotor produces. As long as our imaginary winding creates the exact same field as the real rotor bars, our model is perfect.
Now that we've made that conceptual swap, the hard part is completely over. We can now apply the exact same analytical principles we just used for the stator to this new equivalent three-phase rotor model.
And just look at the incredible symmetry that emerges from this. The equation for the total per-phase rotor inductance, LR, has the exact same form as the stator equation. It's made up of a rotor leakage inductance, LLR, and a magnetizing inductance, LM. And this is critical. That LM is the very same magnetizing inductance from our stator model because it represents that mutual flux path through the air gap that is shared by both.
So, we've gone through this whole detailed derivation for LS and LR. What's the ultimate payoff? Why is this model so fundamentally important to us as engineers?
Okay, let's pull it all together. We started by splitting inductance into two pieces, the bad leakage flux and the good magnetizing flux. We used the machine's perfect physical symmetry to create a simple, elegant model. And we made that brilliant conceptual leap of modeling the complex rotor as a simple winding. And what's the result? These two elegant equations for LS and LR. Now they might look simple, but they are the absolute foundation upon which all modern, high-performance motor control is built.
This static model we've built is our essential foundation, but it also perfectly sets up our next and, frankly, more exciting question. What happens when we introduce motion? How do these inductance values, interacting with resistance and speed, actually govern the production of torque and the dynamic response of the machine? Well, that is where we're going next.
All right, everyone. In this explainer, we are going to get right into one of the most fundamental concepts in electric drives. We're going to deconstruct the inductances that really define an induction machine's equivalent circuit. We're going to build this entire model right from the ground up, starting with the absolute basics of magnetic flux.
So here's our game plan. We'll kick things off by understanding the stator's magnetic flux and how we can actually put some numbers to it. Then, we'll tackle the tricky part, the rotor. We'll figure out how to define its inductance and finally bring it all together into one clean, unified circuit model.
Okay, so to begin our analysis, let's imagine we're looking at the stator with the rotor completely disconnected, open-circuited. By simplifying things this way, we can focus on one single question. Where does all the magnetic flux from the stator windings actually go?
So when we pump current into a single stator winding, let's say phase A, just like in this diagram, that current generates a magnetic field. But here's the catch. This field doesn't just take one simple path. Nope, it splits into two very different components. And really getting a handle on these two paths is the key to the whole thing.
First, we have what's called the magnetizing flux. Honestly, you should just think of this as the working flux. It's the part that does all the heavy lifting. It's the component that successfully makes the jump across the air gap from the stator to the rotor. This is the flux that's responsible for inducing voltage, for producing torque. It's the critical communication link between both parts of the machine.
Now, the other side of that coin is the leakage flux. This is the flux that, well, doesn't quite make it. It never crosses the air gap. Instead, it just takes a little shortcut, looping right back through the stator without ever interacting with the rotor. This leakage flux, it doesn't produce any useful torque. It's basically an inherent imperfection that we have to account for in our model.
Okay, so now that we have a feel for these two physical flux paths, let's see how we can translate them into a precise mathematical model.
The magnetizing inductance for just a single phase is based completely on the machine's physical build. What this equation is telling us is that it depends on things like the number of stator turns squared, the rotor length, and the air gap radius. But notice this, it's inversely proportional to the air gap length. That means a smaller air gap gives you a higher magnetizing inductance. But of course, induction machines don't run on a single phase. They run on a balanced three-phase supply.
So the total magnetizing effect isn't just from one phase, right? It's from the combined rotating field of all three working together. And it turns out this results in a total per phase magnetizing inductance, Lm, that is exactly 3/2 that single phase value. This 3/2 factor is super important. You are going to see it pop up all the time in three-phase machine analysis.
And that brings us to the total stator inductance, which we call LS. It's actually a really straightforward sum. It's just the leakage inductance, LLS, plus that per-phase magnetizing inductance, Lm, that we just figured out. This one parameter nicely packages both the non-ideal leakage part and the useful working part of the flux.
Great, we've pretty much got the stator characterized, so let's switch gears and turn our attention to the rotor. The really common squirrel cage rotor, well, it presents a bit of a modeling challenge. I mean, seriously, look at this thing. It's not a nice, neat set of windings. It's just a bunch of conductive bars all shorted together by end rings. How in the world do you turn that into a clean circuit model with inductances we can actually calculate?
This diagram here shows you the physical reality. Mechanically, it's brilliant, it's robust, it's simple, but from an electrical modeling point of view, it's a real puzzle.
The solution, it turns out, is just incredibly elegant. What we do is we conceptually replace that messy cage of bars with an equivalent three-phase winding. We just imagine a set of windings on the rotor that perfectly mirrors the structure of the stator. It's this powerful bit of abstraction that makes the whole analysis possible.
So, by using this equivalent three-phase model for the rotor, the job of defining its inductances becomes way simpler. In fact, it's almost a perfect mirror image of what we just finished doing for the stator.
Now, listen up, because this next point is probably the most critical concept for tying our whole model together. Think about it. For flux from the rotor to link the stator, it has to cross the exact same air gap as the stator's magnetizing flux. That path is shared, and this simple physical fact has a huge implication for our circuit model.
And here's that implication. Because the path is the same, the per-phase magnetizing inductance, Lm, is absolutely identical for both the rotor and the stator. We use the exact same value. This symmetry is the magic key that lets us create one unified model.
So because of that beautiful symmetry, the total rotor inductance, Lr, follows the exact same pattern as the stator's. It's simply the sum of the rotor's own leakage inductance, LLR, and that same shared magnetizing inductance, Lm. The structure is perfectly identical. All right, we have now defined all the pieces of the puzzle. We've got a model for the stator, we've got an equivalent one for the rotor, and they're both built around a common element. So let's put it all together and see what the final unified circuit looks like.
And there it is. You can see the per-phase stator circuit and the equivalent rotor circuit right next to each other. They look identical, don't they? And that shared inductance, Lm, that's the magnetic bridge that couples them together, just like the air gap flux physically couples the stator and rotor in the real machine. So if you only take one thing away from all this, let it be this. Despite its complex physical nature, the induction machine can be simplified in this really brilliant way. We can model it as two separate circuits, one for the stator, one for the rotor, that are magnetically coupled through a single shared parameter, that magnetizing inductance, Lm. Now, this whole analysis we just did was based on a static, open-circuited view. It gives us our fundamental building blocks. But it leaves us with a huge question, right? What happens when the machine is actually running, when the rotor is spinning at a different speed than the magnetic field? How does this neat little model evolve to account for slip and dynamic operation? Well, that's where the real power of this equivalent circuit truly comes to life.
Have you ever wondered how we can possibly predict, let alone control, the complex behavior of an electric motor? Well, it all starts by building its mathematical model. And today, we're going to build that model right from the ground up, starting with the physical machine itself.
And this right here is the core challenge for any controls engineer. How do you translate a physical object, this hunk of metal and wires on the left, into a predictable, useful mathematical model, like the circuit you see on the right? In this explainer, we are going to build that exact bridge.
So here's our game plan for today. We'll start with the basic modeling assumptions. Then we'll really dig into the stator inductance and this idea of mutual flux. After that, we've got to tackle the rotor, which is a whole different ballgame. And finally, we'll put it all together to get our complete model. Let's get to it.
All right, first things first. Before we can analyze a single thing, we've got to set some ground rules. We need to clearly define the initial conditions and the assumptions for our system.
Okay, so we're starting with two really key assumptions for looking at the stator. First, the neutral point isn't connected to anything, which means the three-phase currents have to add up to 0. And second, for now, the rotor is just sitting there. It's present, but we're going to treat it as electrically inert.
Now for the fun part, stator inductance. To really get what's going on, we have to break the inductance of a single phase down into its most basic parts.
You can think of the total self-inductance as being made of two different pieces, and it all depends on the path the magnetic flux takes. You've got leakage flux, which kind of just loops around its own coil, and then you've got magnetizing flux, which is the important stuff that has to jump across the air gap.
And this picture just lays it all out perfectly. The leakage path, that's the blue line, is basically wasted flux. It doesn't do any work for us. But that orange path, the magnetizing flux, that's the good stuff. That's the working flux that actually makes it across the air gap to interact with the rotor.
And this magnetizing inductance, it's not some magic number we pull out of thin air. It is literally determined by the physical size and shape of the machine. Things like its radius, its length, and most critically, the size of that air gap. That's where all the energy gets stored.
So far, we've just been looking at a single phase all by itself. But that's not the whole story, is it? Now we have to account for how the phases actually interact with each other. And that brings in this crucial idea of mutual inductance.
So what happens when we pump current into just one phase? Well, its magnetic field doesn't just stay put, it spreads out and links up with the other windings. And the amount of that linkage? It's a direct result of the physical angle between those windings.
And it all boils down to pure geometry. No joke. Because those windings are physically placed 120 degrees apart, the mutual inductance turns out to be exactly negative 1/2 of the magnetizing inductance we just talked about. It's just simple trigonometry.
Now this is where the magic really happens. We're going to walk through these 4 steps and put everything together. We'll define the total flux, we'll plug in our term for mutual inductance, and then we'll use that balanced current condition. And when we do, something really fundamental about how these 3 phases work together just pops out.
So here's the big takeaway. The effective magnetizing inductance that any single phase actually sees is amplified by 50%. It's 1.5 times bigger. Why? Because the other 2 phases are actually helping it out constructively. This 3/2 factor is absolutely fundamental.
And that brings us to our final, beautifully clean expression for the total stator inductance per phase. It's just a simple sum, the leakage part plus that new 3-phase magnetizing part we just derived.
Okay, we've successfully modeled the stator. We're done, right? Not so fast. Now we have to deal with the rotor, and with its squirrel cage construction. Let me tell you, it's a whole different kind of beast.
This is a real head-scratcher. The stator has these nice, neat, countable windings. But a squirrel cage rotor, it's just a bunch of solid metal bars that are all shorted together at the ends. How in the world are we supposed to apply our same inductance principles to that?
The solution is actually super elegant. It's basically a mathematical trick. For the sake of our analysis, we say, okay, let's forget the physical cage for a minute. We're going to replace it with a set of hypothetical, perfectly distributed 3-phase windings, just like the stator has. And here's a critical little detail in this assumption that makes our lives so much easier down the road. We decide that this hypothetical rotor winding has the exact same number of turns as the stator. This choice of a 1-to-1 ratio gets rid of all sorts of messy transformation ratios in our final equations.
So, with our stator modeled and this new equivalent rotor model established, we finally have all the pieces we need to assemble the complete circuit representation of the entire machine.
And what's really cool is this. Because that magnetizing flux path through the air gap is shared, the Lm we figured out for the stator is the exact same Lm for our new equivalent rotor. The only new term we need is the rotor's own specific leakage inductance.
And there it is, the whole shebang, the complete phase variable model. Every single inductance parameter you see in this circuit is something we've just derived from first principles, starting from the machine's actual geometry. This circuit is the foundation for everything that comes next.
So let's do a quick recap of the new vocabulary we've established today. Each one of these inductance parameters is a crucial building block. You're going to use these to construct the full dynamic matrix equations that really describe how this machine behaves.
So we did it. We built our complete model. But as you can see, it's pretty complex. And this leaves us with one final huge question. How can we transform this complicated model into something simpler,
something more intuitive that we can use to design really high-performance controllers. Well, that's the puzzle we're going to tackle next time.